Okay, let's go ahead and answer these. So, how are you going to calculate your pH?
Negative log.
Negative log of 2.59 e negative 5 close parentheses. So before you do the calculation, the pH should be between what and what? Bless you.
4 and 5.
4 and 5. So since it's 10 to the negative fifth with a little bit of extra acid, it's not pH 5, it's less than that, it's pH 4 something or other. So if I go negative log 2.9 or 2.59 times 10 to the negative fifth, I get 4.59 for my pH. And then if I take that and add it to 14, I get my pOH is equal to 9.41. And then I get hydroxide ion concentration. That's 10 to the negative 9.41. But if you want to write that in whole number, then you just type that into the calculator, 10 caret negative, that's, and so this is also equal to 3.86 times 10 to the negative 10th. Okay, so this time we've got a pH. So if my pH is 2.36, then my H plus ion concentration is 10 to the negative 2.36, and my pOH is that minus 14, so 11.64. And so then my hydroxide ion concentration is 10 to the negative 11.64. Are we good with those? What's the pH of a 2 molar hydrochloric acid solution? So it's negative log of 0.2. So negative log 0.2, 0.7 is my pH. And so then of a hydroxide ion solution, it's going to be 13.3 is my pH. Where did I get that number from? Yeah, so if I took the negative log of the 0.2, I'd get 0.7, but that's the pOH I just calculated. So then subtracting from 14, so you get that 13.3. All right. And then the nitrous acid solution. So why did I give you like no space for the prior two, but you need a little space for this next one?
It's more work than the first two.
Why? Because it's a weak acid. Okay, so because it's a weak acid, I can't just take the negative log of the concentration because it doesn't fully dissociate. So I'll have a Ka value, and the Ka is going to be equal to H plus. And since it's nitrous acid, it's NO2 negative, and then NHNO2 for the bottom. Do you guys know what the Ka is?
5.62 times 10 to the negative 4. I don't know.
So that table will be on the test, by the way. So you're not memorizing any Kas or any of that garbage. It's just going to be there. So here's my Ka. So my dissociation, my ratio of dissociation, and what I don't know is my concentration of H plus, and I don't know my concentration of nitrite, but I do know they're the same. And then my concentration of the acid was 0.2. So I've got X is equal to the square root of 0.2 times 5.62 times 10 to the negative fourth. So square root of 0.2 times 5.62 e negative 4 close. And I got 0.011. So if I
Okay, I
take
have a question before you keep going. So what are we calculating with that? Before we go into the negative log.
what is that X? That's your question?
That's the molarity of
right?
That's the molarity given that it doesn't completely dissociate, is that what,
Of H plus.
of the H plus?
Yep.
Okay.
So where did that 5.62 times 10 to the negative fourth number come from?
The Ka.
Where did that come from? Don't say the table.
That's the amount, that's the rate at which it dissociates in,
So where did it come from?
it came from
Don't say the table.
1 times 10 to the negative 14.
No. Somebody took some nitrous acid and put it into a container and then checked what the concentration of the H plus ion was, or checked what the concentration of the nitrite ion was, and then they're the same, and knew what the concentration of the nitrous acid was because they put it in the water, and then they calculated out the Ka. Does that make sense?
So that's based off of somebody doing the experiment already. And
Yeah, somebody did the experiment and calculated or measured the H plus ion concentration and the nitrite concentration, and then knew what the concentration of the nitrous acid was because they made the solution. And then they came up with this Ka value. So once I know what the Ka value is, that's telling me my ratio of dissociation. And if I know that the acid's concentration is 0.2, and somebody already did the Ka work for me, then I'm just calculating what the concentration of the two things in the numerator are. And so once I get this 0.011, that's telling me that the H plus ion concentration and the nitrite ion concentrations are both 0.011. And so then once I have that, now I know my H plus ion concentration, so I just take the negative log of that, and there's my pH. So if I go negative log of 0.011, negative log 0.011, close, enter. I get, we got 1 sig fig here. I guess it's 2.
I was going to say, is it 2? Even though the zero's not there, there's a decimal, right?
Yeah, but we started here.
Right.
Yeah, even if the 0 was in front, it'd still be 1. This right here, this guy, the 0 in front doesn't mean, is not a significant figure.
Right, okay. So it is just 1.
So how does this nitrous acid question relate to this hydrazine question? It's a weak base, so I do the calculation the exact same way. But when I calculate all this out, it's going to be backwards, right? I'm going to be counting my hydroxide ion concentration and my POH. So then I'll just subtract from 14 or divide by 10 to the negative 14. So my KB is going to be, I'm just going to write, doesn't actually really matter.
Nitrogen and hydrogen.
0.26 times 10. It's a negative sixth.
Yeah.
It totally and completely, I do not care that you know that the cation for this reaction is that N2H5 plus. How do you know that that is what it is, though? How should you know that? Why is N2H4 a base? That list of weak bases, what do they have in common? All right, what? Say again?
They all have nitrogen in them.
They all have nitrogen in them, and nitrogens all have that lone pair of electrons. That lone pair of electrons can be used to donate to make a bond. So where's the H coming from that's now on this hydrazine molecule? Out of the water molecule. And you don't see the water molecule because what's the percentage of water in water? 1. It's 100, so it just thrown out. So this looks a little odd because the water molecule is missing. It would be in the denominator with the hydrazine, but you just don't put it. So what happened was the hydrazine came in and a couple of electrons off of one of the nitrogens yanked an H off of the water molecule, leaving OHs behind. Do I care that you know that? Sorta. I would like you to realize that that's how the weak bases all work. But what I really care about is I put this base in there and I got a hydroxide and something else up top, a cation. That's really what matters. So before I had put this, we were talking about, right? I said this is the generic formula for all weak acids. I've got an acid, it's weak, I put it in, I get an H plus and I get some anion. Do I care what the anion is? No, I just know that there is one there. So the Ka for this is gonna be H plus, A negative. And why is it that I don't really care what the anion is? Because I'm calculating pH, and pH is just a measure of this thing. And I know I'm getting one of those and an A negative on the other side. And I don't really care what the A negative is. It's got to be there, but its presence, I mean, it could be any A negative. It's not going to affect the pH.
Well, we know it's going to be the same as the H plus.
We know the concentrations are going to be the same no matter what, so I could care less what the actual polyatomic ion or whatever it is consists of. And the same thing goes along with the base. What I care about is in the numerator, there's a hydroxide, and I need to solve for the hydroxide ion concentration. So I'll have X and 0.2. So all this works out the same way, and so I'll get X is equal to the square root of 0.2 times 1.26 times 10 to the negative sixth. And what do I get here? Square root of 0.2 times 1.26 e negative 6 close parentheses equals. And I get 0.0005. What is that the concentration of? Or what is that? It's this is that, right? And that is that thing, right? So it's not pH or POH, it's actually OH concentration. So what can I do with it? I can take the negative log of it, and what do I get?
Three.
3.3? Sure. I get 3.3, but what is that?
That's the pH.
POH. Because remember, this is a base. Yeah.
Base.
And so then the pH is what?
11.7.
Yep, 10.7. Again, for the acid, base, conjugate potassium hydroxide, and bromic acid. So KOH aqueous plus HBRO3 aqueous, KBRO3 aqueous, and water, liquid, base, acid, conjugate base, conjugate acid. The acid and base on the left-hand side are pretty simple. There's a hydroxide there, so that's the base. There's a acid there, so that's the acid. How do I know that let's say the conjugate acid on the right-hand side is the water molecule? What's the easiest way to tell?
It's the only molecule with a hydrogen.
That is the easiest way to tell. If there's a molecule with a hydrogen on it, that's the only thing that could donate a hydrogen, so that's got to be the acid. And then conversely, the other thing has to be the conjugate base. How do you know, or which acid is stronger, acetic or hydrocyanic? Acetic
Acetic.
How do you know that the acetic is stronger?
I looked at my table,
And what did the table tell you?
it told me that acetic acid is more acidic than hydrocyanic acid.
But, I mean, does it actually say that? Hey, acetic acid's stronger, weak acid?
It says that in the way of numbers.
Okay,
like
so-
saying acetic acid is 10 to the negative 5 and hydrocyanic acid is 10 to the negative 10.
So the Ka value for the acetic acid is larger.
And that's what.
Yep, that's it. So that's telling you the bigger the Ka, the larger dissociation I have for that acid. So the acetic acid dissociates 100,000 times more easily than the hydrocyanic acid. Okay, I've got 30 milliliters of 0.1 molar hydrochloric acid, and I'm going to add this to 600 milliliters of water. What's the resulting pH? So what's nice about this? It's a strong acid.
Strong acid.
So there's a couple of ways you could do this, okay? I think the easiest thing to do is just to use the dilution equation and then calculate the pH off of that. So the dilution equation, remember, is concentration 1, volume 1 equals concentration 2, volume 2. Now, there's a tiny bit of trickiness to this. So what is the initial concentration? It's 0.15 molar. Great. And the initial volume? 30 milliliters. Great. What is my final concentration? I don't know. That's what I'm going to calculate. What's my final volume?
630.
The trickiness is it's 630 milliliters. Not 600 milliliters, because I added it to it, right? Okay, so then my M2 is going to be 630. Oh, no, it's not. It's going to be 0.15 times 30 divided by 630. And so I get 0.007. And this is the molarity of my HCl, right? So since it's hydrochloric acid, it's a strong acid, then I can just take the negative log of that value. And I get a pH that's equal to 2.15. Whatever, 2.15. That's the calculated value. So is that a big deal? Did the pH change a lot? It was pure water, right? So the pH was 7, and I added
Yeah.
30 milliliters of a pretty dilute solution of hydrochloric acid, and the pH changed how much?
4.85.
Near 5, right? So near 50, so near 100,000, close to 100,000 times more acidic by putting this a little bit in there. Okay.